So I've not gone through the data collection reports. I'll try and get through them this weekend and hand back with some feedback on Monday. Is the plan. So let's just, while I have this up, let's quickly look at the schedule. So we're right here. So we're on the last part of the frequent items part of the class. So we're just spending a week on this. Although we'll come back with some games from this section in some of the later sections of the class as well. So if you haven't been paying attention, the clustering homework is due in 1 week. So if you have programming experience, it should probably be pretty easy. If you don't, it won't. It'll probably take a little bit longer. And then it's the last day before spring break, so we have a couple classes off, and then there'll be a homework assignment on the frequent items. The plan for this is that this one will not be as long, so you can focus more on the project in the second half of the class. We'll also have another homework assignment on the regression section, which will start next week on Monday. It's kind of be longer, covering several kind of topics. And hopefully this homework is not too hard as well. It's going to be worth the full 20 points again, and hopefully it's not going to take as long. You're not going to have to go through the details of getting, it'll be kind of fairly straightforward doing stuff in like MATLAB for the most part. And then there'll be one more assignment at the end on the graphs, which is like this link analysis part. So this one, what I've done in the past is this one's been optional, where you can do it and it will have, hopefully it won't be too hard, and it'll have several bonus, and you can average that into your grade if you want. If you don't do it, it doesn't. You just average the homework assignment that you've done. So I'm hoping the second half of the semester you'll really be able to focus on the projects, but the first Wednesday after you get back, the intermediate report will be due. So I want to see some progress at that point so I can direct you on what you need to do to finish up the project. So I'm hoping, you can kind of get some stuff working, get the basic idea, kind of figure out what's going to be hard, what's going to be doable, and I can say, here's what you should do to figure it. I don't expect everything done, but I hope you kind of have gotten started at this point, and this is worth some non-trivial amount of points towards the project, so you need to actually do something. Questions on the schedule? All right, so, yeah.
What is the feedback on that last optional homework you can actually downgrade?
Yeah, it's possible. I don't think anyone's done that. So the last one, is not too hard. So if so at one point so I've heard about this this class where you get this professor had this grading system where every test was multiple choice. There are 4 options. You could leave it blank and you can get 1/4 of a point for any question. And so there's someone in the class who needed like 28% on the final exam to pass. And he took it and got like 20% and ended up not passing the class. So I could be nice if you, I think maybe last semester that happened and I didn't average it in. I think that probably if it affects the grade between the boundaries, I'd rather see you do effort on there, and I'll probably be a little bit nicer if it comes down. So you could decrease your grade, but you'd have to do something really offensive, right? Like if you wrote in answers that you knew would make me upset or something. At the same point, if you shot the moon and got really, really bad, then maybe I would give you punishment. I don't know. So I'll encourage you to do it. So hopefully you'll find the assignments are you're actually learning the material a bit better. So that's kind of the point behind them. I hope you're doing them to learn more than doing them to get points. So you'll kind of walk you through some of the things we'll do with graphs. Okay. So cool. So we're going to talk about, so on Monday we talked about frequent items, and this was a very kind of simple idea. You had these multi-sets, you were seeing them in a stream, and you want to find the things that occurred, many times. These were the important items. Today we'll be talking about an extension of this problem called frequent item sets. Okay, so instead of finding individual things which occur a lot, we're going to find examples of sets of things which occur a lot. So we want to find essentially things that occur. All right, so some classic example of this is, so say like purchases at a grocery store. Okay, so when customers go to the grocery store, they'll buy like more than just one item. Sometimes, sometimes if I go to the grocery store, I just buy one thing, but every time my wife goes, she buys like 40 things. I don't eat all first. I go and grab one thing and I'm out, but usually maybe I'll buy 3 things, right? So I'll go to the grocery store and I'll buy 3 things in my set. I'll buy beer, I'll buy diapers, and I'll buy some milk, right? So my wife sends me to the store. What she wants me to get is diapers and milk, and I also get some beer, right? So maybe this is what happens. So this is my trip to the store, and then there's another customer who comes, and they go and they buy. They're also sent to the store by their wife, and so they go and they get some diapers, they get some bread, and they get some soda, something like that. And then sum it up. Some other guy goes to the store, and they also get diapers. They get some meat, and this person also gets some beer, right? So if you see a lot of these things, what you might see is that supposedly these strange relationships where you might be supposed to find, you see that people who buy diapers also often buy beer, which you might not expect. There are different categories of things in the store. All right. So this is a classic example. So and the typical, and what we'll talk about today is something called the Apriori, the Apriori algorithm. And so it can look at these sets of these sets and find things which co-occur together. So this is I'm kind of speaking about this because it's a very classic algorithm from data mining, and it's one of the things in like most of the textbooks. It's taught in most classes. I find there's a really cool trick behind here, which is really neat. And then there's lots of variations that have been built on top of this, and you can spend several lectures going through the variations. I'm going to show the cool trick, and then you can kind of imagine some of the variations, and we will talk about one kind of way we can kind of speed this up. But there's lots of things to do out here. Okay, what we want to do is look at these relationships and find things which happen to co-occur at the same time. So the diapers and beer occurred here, and the diapers and beer also occurred here. So there's I wrote this up because there's a classic example in a textbook that talks about this, and then there was apparently someone had done some study, and they claimed this was here, and then people did follow-up studies and they didn't actually find this correlation. But there was supposed to be a correlation where when people bought diapers, they also bought beer, so then grocery stores would go and put the beer next to the diapers, right? So if you went in and the idea was, if people are likely to buy these together, they may go in to buy diapers, and if they see the beer, then they're likely also to buy that. If they didn't see it, they might not. So grocery stores can take advantage of these relationships. So another place you might see this is like on Amazon, right? So you see people who purchase this also likely purchase these other products, right? So they're using some variation of this thing. They have lots of different customers, and they say, you know, they may keep track of your whole history of purchases, but they're probably interested in purchases within some window, and they group these together in some time window as some set, and they want to say these two things were bought, you know, maybe in the same order or within a month of each other. And they can advertise other things, and doing this will hopefully increase their sales. And so we're going to be talking about, again, very basic models here, but Amazon has really invested a lot of engineering into this to try and increase their sales by saying, hey, you may also need this other product if you're buying this. So, you know, whether you need these two things together may not be true, or it may be true, but you may end up buying these things together. So you want to find things that can co-occur together. From this, you can maybe say, and so I'll say, maybe you can say that there's some causal relationship. So, you know, if you do one thing, you're also buying another. So if you're buying, so if you're buying spaghetti, you may also buy spaghetti sauce, right? These things are actually, you're buying spaghetti sauce because you're buying spaghetti, right? So there may be a causal relationship. Now, understanding the direction of this causal relationship is a lot harder to do. But this is kind of the start. What you want to do is find things which commonly occur together, so you can start to know which things to examine. There may be a causal relationship. And doing this is a much more challenging problem. And there are probably various techniques to do it. We're not going to kind of get into trying to learn this causal relationship. This is whether you can actually do this, whether you can actually ever learn and really say something is causal, that's a whole nother story. But so what this will be guided by is, you know, this can be a really large problem. So what we're going to say is that, make sure I get my notation right here. So we're going to have, each of these is going to be a tuple. We're going to see this, call this T1, T2, up to Tm. So we're going to have m of these tuples. So these are going to be sets. So we'll have a set of tuples. And so they don't all need to be the same size. Like I may buy 3 things, and my wife might, you know, is going to buy 40 things. So they're not all the same size, but they're probably, none of them are probably too big. Like another possible example thing could be each of these tuples is going to be a sentence, and each of the elements is going to be a word in the sentence. Which words co-occur together in sentences? Or you can say k-grams, which k-grams within a sentence co-occur together. Right? So likely the ones that overlap, but you may find other things beyond that. And then you also want to say each tuple Ti is going to be a subset of some domain n, right? So you're going to have n. So this is the number of products. So if you're a grocery store, you're going to have a lot of different things that you sell, but you probably know every single thing you sell. You have a database of these things, right? This is not too big that you don't know what it is. On Amazon, they sell a huge number of different items, a huge number of different books, and they know all these different things. They know this set. Okay, this set of different products you can have. There may be, maybe words in a dictionary, or words, strings of letters separated by spaces on Twitter. They may not actually be words, but there's some large set, but this is some finite set of things we can examine. Okay. So if we want to find the things which occur together in all these tuples, this can be a pretty big problem, right? If there are, so we want to look at all these tuples of items. We want to find the things which are co-occurring here, right? So if we just want to find sets of two things which occur together, that's one thing. We may want to find sets of three things that occur together. Like if you're making cookies, then you probably need. So if I'm making cookies, I'm just buying the cookie mix, and then I probably need like milk or something too. So I cookie mix and milk, but my wife makes it. There's flours, there's chocolate chips, there's eggs, there's all sorts of stuff that goes in together. You can find these larger relationships, other than just pairs. You can find sets of three things, sets of sets of 5 things which occur together, right? So the number, so if it's, if you're, if you're looking at a co-occurrence, right, this is, I probably spelled this wrong. Okay, so that means it's, this is two things together, then this is going to be n choose 2, and this is roughly n squared different pairs of things, right? So, a grocery store can keep track of all its products, but it doesn't want to keep track of all pairs of its products to know which ones occur together. This number really explodes. If a grocery store may carry, maybe 10,000 items, but it doesn't want to keep track of something for 10,000 squared. Right, that would be, what would that be like? Like 100 million? Yeah, it doesn't want to keep track of 100 million things, right? This would really be a lot. And if they had 20,000 things, then this is 400 million. They don't want to keep track of all these relationships. And if you want to find 3 things that are found together, then if you're going to have 3 things together, then this is going to be n choose 3 possibilities, and this is going to be roughly n cubed, right? This number is even huger, even larger. So you don't want to keep track of something for all of these triples together to see if these co-occur with each other. Okay, so we somehow want to do this as these tuples are coming in, or as we have these tuples, we want to examine this history and do this in some way that's efficient. This is probably a really large set. The set of all receipts on Amazon, these orders together, the sets of all receipts from customers, they really can go through a lot of customers over the last year. So we want to kind of process this quickly and find these co-occurrences. So there maybe are, so what people work on, how they work on this data is really dictated by what they can compute efficiently. Because if they can't compute it, efficiently, it's going to take a long time to do. So this is kind of what we're going to talk about is based on how we can perform this sort of analysis and quickly to find the items which occur very frequently. Okay, and the pairs and the triples that occur very frequently. Okay. So basically, how does this work? So we want to find the pairs which occur frequently. So let's set some thresholds. So let's say that we want to find pairs occurring at least 1% of all purchases. Okay, so they should be 1% of all tuples, right? So that means that so they occur in m over 100 tuples. Okay, so these are, let's define some threshold, and we want to find these sorts of pairs. Okay, so what do we know about these pairs? Well, what can we, instead of looking at all possible pairs, this is going to be some, if we want to find these, knowing that they must occur in m over 100 tuples, we can use this fact to actually find them more quickly, to find all of them. So let's say that beer and diapers occurs in 1%, at least 1% of all the tuples, right? So then what do we know about both the product beer and the product? So just the product beer. So what does that say about the product beer? Yeah, that's right. So this implies if a pair is a purchase in at least 1% of all tuples, then each of the items must also be purchased in 1% of all tuples, right? So this is really useful, actually. So the first thing we're going to do is find all find all items occurring 1% of the time. Okay, so we want to scan and find all these items. And so, this is something that we talked about on Monday, how we can do this quickly. So we talked about this thing where we can scan over all of this data. So maybe these data is stored on disk. We want to scan over all of this data set and find all the things that occur at least 1% of the time. So we can do this by keeping actually a fairly small summary. Well, we don't need to store, we don't need to kind of keep track of all n of the tuples, although n may be something small enough to fit in memory. We could keep a counter for each of these, or we could use like the streaming algorithm and keep kind of this smaller set of counters and still guarantee to say we're between, we might accidentally get, if we set the error there to be 1/10 of 1%, then we can say we'll guarantee to get everything 1%, and we might get things that are like 1.1%, or that are only say 0.9%, that are only 0.9% when we thought they were 1%. But that shouldn't be too many items. There can't be too many items which are only occur 1% of the time. So the first thing is we find all of these items, and so this is going to be, we'll call this the set 1, and this will be a subset of all of our items. And so, because, so this is slightly different than the guarantee we talked about on Monday. This was, every time we saw an item, that was the only item in the tuple. Now we're saying, we're counting the fraction of tuples that it occurs in, and you may have multiple items. Here I have 3 items in each tuple, right? I could have many more items. Well, most of these sets are usually not too big. So maybe instead of, our errors on m, we have, the average size of the tuple may be 10, so we need to have the error relative to 10 times m, the number of tuples instead. But you can still kind of do this. It's still, the number of these often occurring items is still going to be much smaller than the full set. So then from here, what you want to do is to construct all pairs, and we'll call this x, y, which are in S1 plus S1, right? So we want to find all pairs which are in this set, which are, both m's are in this set. And so now, this is going to be, the size here is going to be roughly the size of S1 squared. But this will typically, in most cases, this is about the size of n, or it's going to be smaller in many cases. So by restricting the set of items that occur very, we only are looking at items which occur frequently enough themselves, then we're looking at a much smaller set on this. Even all the pairs here is still going to be, so in many cases, this is roughly less than or equal to n. So we haven't really increased the size of the set we're considering too much. And so then we go back and we make another pass of the data, and we find, and we look at all the tuples examining this set of these pairs. Yeah.
Depending upon the percentage, like here we are choosing 1%.
Yeah.
Can't we make an upper bound on this?
So we, so you're right. So we can make an upper bound on actually the size of the set, right?
Yes.
So if each tuple was of size 2, right, then, so you can say then that there can be at least, there can be at most 200 items that occur 1% of the time, right? So why is this the case? Because if more than 200 items occurred 1% of the time and each tuple was size 2, then then you would have more. So let's give it like a hard example here. So let's say m is equal to 1,000, right? So if something occurs 1% of the time, it must occur in at least 10 of these tuples, right? And so let's say that each, so let's just give an example where each ti has the size of ti equals 2. So that means the total number of all items in all sets, so the sum of ti, all the items in all sets here is now going to be 2,000. We only care about items which occur at least 20 times, right? So that means that if an item occurs at least 20 times, then we're gonna for every one of those we're gonna take out at least 20 of these items. They can't be a different item because we're looking at the number of distinct items which can occur at least 20 times. So what we then say is that. So each item has to occur at least 10 times, sorry. So if it occurs 1% of the time, it's at least 10 times out of the 1,000 tuples. So then we can say that 2,000 divided by 10, because each of the items can only occur 10 times, we only get 200 possible items. So this number would be greater than S1. So the set here cannot be too large. Okay, so it's a little bit different if you don't have a bound. In order to do this analysis, I needed to say the size of the tuple is at most 2 in order for this to work. If I don't have a bound here, then I can kind of say what is the, what I really need is a bound on the sum of all the sizes of the tuples. And then I divide, and then I take 1% of this number, whatever thing I want to occur at least 1% of the time, I get 1% of this number, and that's how many possible items I can have. So you can see you can roughly, so I still only 200 of these, but I started with 1,000, right? So this wasn't a huge gain. But if I started with, let's change this analysis now. Let's say I started with m equals 10,000. I still said each tuple was size 2. So then the sum of all these was 20,000. And now, if an item occurred 1% of the time, it happened, I had 20,000 here. That means it happened at least 100 times. I still get 200 here. Okay, because I increased the total number of items I see in all the tuples, but I'm also increasing the number of times each item occurs for it to be interesting. So I still get 200. Now, 10,000 down to 200 is a really big drop. And if I keep this value at 1% and this goes up to 100,000, I still get 200 here. So I'm still getting a big drop here. Now, if this is instead of 2, this is 10, then instead of 200, this is going to be 1,000, right? So, but again, this is a very conservative bound. This is kind of a worst case thing. In practice, this number may even be much smaller than this. And typically the case is that this number squared is about the same scale as the number of items we have. If it's not, you may actually decrease this 1% factor. If you make this too small, then we don't get much. Then you can get this being much bigger than n, and you can run into some trouble. Okay, so after this algorithm is kind of what you'd expect. Once you have all these pairs, and you don't have too many of these pairs, you can then go and you know that any pair that occurs frequently must be made up of one of these pairs out of the set S1. And so then I can go and find all pairs which are occurring greater than 1% of the time. And I can put this in set S2. Right, so now this S2 is a set of pairs. So this will be a subset of, let's say, of S1 cross S1, which is a subset of N cross. And this is being a little sloppy. I don't want to occur the same item. Or maybe people buy the same item twice. We want to keep track of that. So these are all pairs here. So I can scan over the data, and I just need to read through the list of my tuples and check every tuple whether it's in a pair and increment the counter for each of these items I have in the set. Okay, so this seems pretty simple, but it has some really big advantages. One is I only needed to read over my data set twice. If this is stored on disk, then the main cost of doing this is actually reading the data, of bringing the data off of disk into memory. That takes longer time than actually kind of running it through the CPU because of this is like what happens when your computer is thrashing. If you're trying to load a really big file into R, it just takes a long time to do it because you can't fit it all in memory. Or the same thing occurs in MATLAB or a lot of other of these programs that if you're using, trying to do analysis on a really big data set, that's often where the problem comes from, thrashing of bringing the data from disk into memory. But if I do it this way, I'm kind of just reading it over, making a pass over it, and so the OS will actually take care of kind of bringing the blocks of data into memory once, and then they throw them away once you've read over them and don't need them anymore. So this actually works really efficiently on large data because of how we organize this. The other thing is that now that we have all of these pairs which occur together a lot, now we can really easily find all triples which occur together a lot. All triples must be made up of, if we want to find all triples which occur at least in 1% of all of the purchases, well then each of the items must be in the set S1, and actually a triple is going to be, X, Y, Z, right? Each of these pairs, X, Y, Y, Z, and X, Z, each of these must be in S2 now. I've already calculated the set, and each of these must be in here. Okay, so I can then say, scan over my data a third time and check for the triples, but before I do that, I can prune and just find the pairs, or just find the triples where every pair is an S2. And usually this set of triples is actually already very small. In fact, before I go and scan it, I can go and say, not just all the triples, I can find all the sets of 4 things where all the pairs that make it up are in the set S2. Because there probably aren't that many triples or these 4 tuples either. Okay, so just to drive this home, I'm going to go through an example here if this wakes up. All right. So instead of, you need it to be sufficiently big for you start to see anything here. So I'll go through this example where I have these 12 tuples, and the sets are of different sizes, and each tuple has something from, this set 0 through 10 in it, right? So in this example, so in this example, I'm going to have m equals to 12, and n equals to 10, right? And in fact, instead of, actually, if I write this notation, it usually means 1 up to n. Well, I'm going 0 through 9, but so we can set n is 1 to 10. Okay, so now how's this algorithm work? Well, I'm going to start by setting up a counter for each of these items. So I'm going to have this table 0, 1, 2, 7, 8, 9. And so for each of these products I have, I'm going to have a counter, and then I just scan through this data set. I can read everything once. So in tuple 1, I'm going to see which items do I have in my set, and we'll keep counters 1. And then in tuple 2, 2, 6, 7. So 2, 6, 7, 9. Tuple 3, 1, 3, 5, 6. Tuple 4, 2, 6, 9, 7, 8, and hopefully